Okay, so the question reads sigma from r equals 1 to n of 2 to the r being equal to 2 outside of 2 to the, what would it be? R minus 1. Okay, so this is sigma notation, and in sigma notation you are looking at replacing the r's with the values on the sigma. And so the left hand side, well, the whole thing actually can be written as, the first one is r equals 1, so you sub in 1 for r. The second term r is 2, the third term r is 3, and so on, and it sums all the way up to 2 to the power of n. And the sum of all of that is 2 outside of 2 to the n minus 1. Now that should be an n up there, not an r, because it's not replaced with r each time, it's just like that. Okay, so in order to find that, we need to first do step 1, and in step 1 we prove true for n equals 1. So the left hand side equals 2 to the power of 1, which is 2. The right hand side is equal to 2 outside of 2 to the 1 minus 1, and that is 2 in the brackets, take away 1, which means it's 2 times 1, which is 2. And so therefore it's true for n equals 1. Okay, in the second step, step 2, we assume true for n equals k, and so we just rewrite the statement that we've got up above us, which is 2 to the 1 plus 2 to the 2 plus 2 cubed plus all the way up to 2 to the k is equal to 2 outside of 2 to the k minus 1. Okay, now that's nice. Step 3 then is when we prove true for n equals k plus 1. This obviously is where we get it a bit more challenging. So that would now read 2 to the 1 plus 2 squared plus 2 cubed plus all the way up to 2 to the k, and then the new term added on is 2 to the k plus 1. And on the right hand side you get 2 outside of 2 to the k plus 1, take away 1. Okay, very good. So firstly, on the left hand side we have 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the k plus 2 to the k plus 1. Now the first terms all the way up to, from 2 to the 1 all the way up to 2 to the k, are equal to 2 outside of 2 to the k minus 1. So that is equal to 2 outside of 2 to the k minus 1 plus 2 to the k plus 1. And this piece here that I've put in a bracket is equal to this piece here, and that is from the assumption step. Okay, so that's where I get that from. Okay, cleaning that up then, we get, what do we get there? Well, we get 2 times 2 to the k minus 2, and we get 2 to the k again times 2, because you can split that as 2 to the k times 2 to the 1, which is the same as that. And so on the left hand side we get, well actually it's 2 lots of 2 to the k plus another 2 lots of 2 to the k, which is 4 times 2 to the k minus 2. Or at that step, if you prefer, you could turn it into 2 outside of 2 times 2 to the k, because there's 2 lots of those, take away 1 because you factorise the 2 out. Okay, if you do it that way, of course, you can simplify it even further and get 2 outside of 2 to the k plus 1, take away 1, and if you do it that way, you'll notice that we've now reached the right hand side. So we've worked the left hand side till it got to the right hand side, and so therefore the left hand side equals the right hand side, which is equal to 2 outside of 2 to the k plus 1, take away 1, and then all of that proves that it's true for n equals k plus 1. So therefore true for n equals k plus 1. Now, because it's true for n equals k plus 1, and it's also true for n equals k, we've proven now that if you can start with 1, then all the other ones above 1 are also true, and because we did start with 1 up in step 1, it's true by mathematical induction. Now, step 4 is the conclusion, and even though there's a really nice fancy one, we will do what the Board of Studies requires, and we will say, therefore, true by the process of mathematical induction, which is a very boring sentence compared to the proper one, but that's what they want, and that's what we will give them. That is it.